In the second half of this review, we are going to focus more on power series and Taylor and Maclaurin series. So first, find the radius of convergence and the interval of convergence for this given power series. So to do this, we apply the ratio test. Notice that this n in the denominator is the part that messes up using the root test. With that n there, the root test just won't work. So find the limit as n goes to infinity of an plus 1 over an. So we have x plus 2 to the n plus 1 over n plus 1 times 4 to the n plus 1 multiplied by n 4 to the n over x plus 2 to the n. Now you're left with a singular x plus 2, an n in the numerator, a 4, and an n plus 1 in the denominator. But x plus 2 has to stay in absolute value bars because x could be a negative number, whereas we know that n is an integer and n is a positive integer, so therefore positive. So as n goes to infinity, this n over n plus 1 ratio will go to 1. So this limit goes to the absolute value of x plus 2 over 4. And by the ratio test, this will converge if the absolute value of x plus 2 over 4 is less than 1, which implies the absolute value of x plus 2 is less than 4. And our radius of convergence is 4. Now to find the interval of convergence, we observe that x plus 2 being less than 4 absolute valued means that x plus 2 is between 4 and negative 4. And take away 2 and we have negative 6 is less than x, which is less than 2. So we need to test at x equals negative 6 and at x equals 2. And if we input negative 6, our series becomes a sum from n equals 1 to infinity. So negative 6 plus 2 will be negative 4 to the n over n times 4 to the n. Now that simplifies to the sum from n equals 1 to infinity, negative 1 to the n over n. And that will converge by the alternating series test. And at x equals 2, we get the sum from n equals 1 to infinity, 4 to the n over n times 4 to the n, which is the sum from n equals 1 to infinity, 1 over n, and that diverges. It's the harmonic series. So in that case, the interval of convergence includes negative 6, but does not include 2. All right, how about for this series? So let's find the limit as n goes to infinity, an plus 1 over an. We apply the ratio test here because factorials just almost always suggest that's what we're going to use. So n plus 1 factorial, x minus 2 to the n plus 1, that's the a sub n plus 1, over n factorial x minus 2 to the n. Well, n plus 1 factorial over n is n plus 1, and then x minus 2 to the n plus 1 over x minus 2 to the n, that's x minus 2. And this limit is going to be infinite, which is definitely bigger than 1 if x is not equal to 2. So this thing will have radius of convergence 0, meaning it converges only when you're summing up a bunch of zeros. And you're going to be summing up a bunch of zeros if this x minus 2 is equal to 0, which means x equals 2 only. That's the only value for which this series converges. So the interval of convergence includes the number 2 and nothing else. Now on the flip side, what if that n factorial was in the denominator? What happens then? So let's apply the ratio test again. So that's the limit as n goes to infinity, 3 to the n plus 1, x minus 2 to the n plus 1 over n plus 1 factorial, multiplied by n factorial over 3 to the n, x minus 2 to the n. So no canceling stuff. So 3 to the n plus 1 over 3 to the n leaves us a 3 in the numerator. We also have an x minus 2, an absolute value bars in the numerator, and an n plus 1 in the denominator. And the 3 and x minus 2 are constants, so we have 3 divided by 3, a constant divided by a big number. That will be 0. And this is less than 1 no matter what x is. Which means that this series will converge for any x. That means your radius of convergence is infinite, and your interval of convergence is negative infinity to infinity. The next thing we discussed was how to find power series for specific functions. Now, this says to find a Maclaurin series for f, and you think, oh my gosh, that means I've got to take derivatives and blah, blah, blah. It's so horrible. But it turns out you were finding Maclaurin series. We just didn't call it that, because when we expressed this as x squared times 1 over 1 minus negative x, and then used the fact that this is kind of geometric, wrote it as x squared times the sum from n equals 0 to infinity, negative x to the n, and then said, okay, that's the same thing as x squared sum n equals 0 to infinity, negative 1 to the n, x to the n. That is a Maclaurin series. So this is centered at 0. It's the power series representation. So that was another way to find Maclaurin series, and you could use repeated derivatives to do so, but it's going to be much, much harder and much harder to see the pattern because you're going to probably make some mistakes along the way. The last thing you should do is multiply this x squared through, and those exponents then add, giving you a sum from n equals 0 to infinity, negative 1 to the n, x to the n plus 2. Now, using that geometric series formula depended upon this number being a 1, so to make that happen, we divide everybody by 8, 4 over 8, over 1 plus x over 8, which is the same thing as a half over 1 minus negative x over 8. So that is the sum from n equals 0 to infinity, 1/2 times negative x over 8 to the n, which is the sum from n equals 0 to infinity, 1/2 negative 1 to the n, x to the n over 8 to the n. And technically, this is not something I probably would require, but it's good to know that it's possible. You could write this as negative 1 to the n, x to the n. This 8 to the n, 8 is the same thing as 2 cubed. So you have 2 cubed to the n, which is 2 to the 3n, which allows you to multiply by that 2. So 2 times 2 to the 3n will be 2 to the 3n plus 1. So that's the absolute bestest way to write this. And let's also find the radius of convergence. So that can be determined here. Because this is a geometric series, we need the absolute value of negative x over 8 to be less than 1, which means the absolute value of x must be less than 8, and a radius of convergence is 8. All right, find the power series for this function using an integral or a derivative. So you observe that the derivative of natural log of 2 minus x is negative 1 over 2 minus x. And so if you integrate negative 1 over 2 minus x, you're going to get back natural log of 2 minus x plus some constant c. And the kicker is that this is something you can find a power series for. And then once you have that power series, you can integrate it term by term. So natural log of 2 minus x is equal to the integral of negative 1 over 2 minus x, which is the same thing as the integral of negative 1 over 2, 1 minus x over 2. And as a geometric series, that's the sum from n equals 0 to infinity, negative a half times x over 2 to the n dx. And separating that out into powers of 2 and x's before we integrate, that'll be negative 1 x to the n over 2 to the n plus 1. Now the 2 to the n plus 1 and the negative 1 are a constant. The thing that's being antidifferentiated here is this x to the n. And so the antiderivative of x to the n is x to the n plus 1 over n plus 1. So this antidifferentiated gives you a sum, n equals 0 to infinity, negative 1, x to the n plus 1 over 2 to the n plus 1 times n plus 1, and then plus some constant c. And since you know that this function has to equal this series, you can use that information to get what c is. If you input x equals 0, on the left side we get ln of 2. On the right side we get 0 plus c. Therefore c must equal ln of 2. There is the power series, or even really the Maclaurin series, because it is centered at 0 for a natural log of 2 minus x. Now it's going to be pretty useful if you know some Maclaurin series and the interval of convergence for some common functions. So for 1 over 1 minus x, this is the sum from n equals 0 to infinity x to the n, or 1 plus x squared plus x cubed, etc. Its radius of convergence is 1. E to the x is the sum from n equals 0 to infinity x to the n over n factorial. That is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Its radius of convergence is infinite. Sine and cosine are alternating series. So sine is negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Or that would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Also r is infinite. Cosine is the derivative of sine. Sum from n equals 0 to infinity, negative 1 to the n x to the 2n over 2n factorial. Or 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. are still infinite. And inverse tan is the sum from n equals 0 to infinity, negative 1 to the n x to the 2n plus 1 over 2n plus 1, or x minus x cubed over 3 plus x to the 5th over 5, etc. Not having factorials there makes a pretty big difference. This r is 1 versus when you have factorials and that r is different. And let's add one thing to this list. Let's add natural log of 1 plus x. That is the sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n, if you start the indexing at 1, If you were to start that at 0, it'd be the sum from n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. The same thing. Also r equals 1. So using the definition, let's find the Taylor series for e to the 2x at a equals 6. So remember that the Taylor series is given by f of a plus f prime of a times x minus a plus the second derivative at a over 2 factorial x minus a squared plus third derivative at a over 3 factorial x minus a cubed, etc. So to find the Taylor series, we're going to need to find a whole bunch of derivatives and look for a pattern. So first, f of x is e to the 2x, and so f of 6 will be e to the 12th. The first derivative of e to the 2x is 2e to the 2x. So f prime of 6 will be 2e to the 12th. The second derivative will be 2 times 2, or 2 squared e to the 2x. Second derivative at 6 is 2 to the second e to the 12th. And by then, hopefully you can see a pattern. The nth derivative will be 2 to the n e to the 2x. And so the nth derivative at 6 will be 2 to the nth e to the 12th. So plugging those numbers into our Taylor series, we have that e to the 2x is going to be equal to e to the 12th plus 2e to the 12th times x minus 6 plus 2 squared e to the, over 2 factorial e to the 12th x minus 6 squared, etc. Or in summation notation, sum from n equals 0 to infinity. Well, the e to the 12th is just a constant. We'll have 2 to the n, x minus 6 to the n, and all that over n factorial. You can also find Maclaurin series using the series that you know and inputting various values. So to find the Maclaurin series for inverse tan of x cubed, we take the Maclaurin series for inverse tan, sum from 0 to infinity, negative 1 to the n. Now this would have usually been x, but we're going to put in x cubed instead, to the 2n plus 1 over 2n plus 1. And you just simplify your exponents, at least just to show to me you do actually know what to do with them. That's going to be x to the 6n plus 3 over 2n plus 1. If you found repeated derivatives and input 0, you would get the same pattern, it's just going to be significantly more painful. And here we have convergence if the absolute value of x cubed is less than 1, because the radius of convergence for inverse tangent says that that x has to be less than 1, which implies that x's absolute value is less than 1, so the radius of convergence is 1. All right, here we're going to take x times the sum from n equals 0 to infinity. Now the series, the Maclaurin series for e to the x would be usually x to the n. Here we're going to have 3x to the n all over n factorial. That's x times the sum from n equals 0 to infinity, 3 to the n, x to the n over n factorial. Or distributing that x through will increase all the powers by 1, making this 3 to the n, x to the n plus 1 over n factorial. As the radius of convergence of e to the x is infinite, this will also have an infinite radius of convergence. All right, sine of x to the 4th, so input x to the 4th into the sines Maclaurin series. So negative 1 to the n, x to the fourth to the power of 2n plus 1 all over 2n plus 1 factorial. And that's going to be the sum from n equals 0 to infinity, negative 1 to the n, x to the 8n plus 4 over 2n plus 1 factorial. And since the radius of convergence of sine is infinite, this will also have an infinite radius of convergence. Now this one, if you're clever, you can actually use the series, Maclaurin series, for e to the x. So you could do this using a definition, which is totally fine. The pattern's pretty easy as long as you remember that the derivative of 10 to the x is natural log 10 to the x. But here's a clever way. Write that 10 as e to the ln of 10. And you should, by cancellation properties, e to the ln of 10 is just 10. Well, those exponents multiply, giving us e to the power of ln 10 times x. And then you can plug ln 10 times x into the Maclaurin series for e to the x. This gives us a sum from n equals 0 to infinity, ln of 10 times x to the n over n factorial, which is the sum from n equals 0 to infinity, ln of 10 to the n, x to the n over n factorial. And just also notice that ln of 10, the quantity to the n, is not the same thing as ln of 10 to the n. So this one means you have natural log of 10 multiplied by itself n times. This means 10 is multiplied by itself n times. Those things are not equal. So you can prove it to yourself using some numbers, like plug in ln of 10 squared in a calculator versus ln of 10 squared in a calculator, and you're going to see that those two things are not equal. I mean, for one, this thing on the right is 2 natural logs of 10, whereas this thing is natural log 10 times natural log of 10. And usually a number squared is not equal to 2 times that number, so this is not true. Those parentheses are actually important. You also should know that you can find integrals that are sort of not findable other ways using infinite series. So to evaluate the integral of e to the x over x, let's think about this as x to the negative 1 times the sum from n equals 0 to infinity, x to the n over n factorial. And then adding those exponents, we have the sum from n equals 0 to infinity, x to the n minus 1 over n factorial dx. And the part you integrate is the x to the n minus 1. That over n factorial is just a constant. So the antiderivative of x to the n minus 1 will be x to the n over n, plus some constant c, which we can't find. And so as an infinite series, this is a sum from n equals 0 to infinity, x to the n over n times n factorial, plus some constant c. And if you're clever, you can find the sum of some series exactly by recognizing that they are Maclaurin series with specific values for x plugged in. So this looks an awful lot like cosine, except for this part there should have been raised to the 2n. So here is how we're going to deal with that. And it's not just change it to 2n, because that wouldn't be the same thing anymore. So if we do make that a power of 2n, the pi has to be raised to the power of 1/2. You can see that when those powers multiply, 1/2 times 2n just gives us n. So this is the same thing as the sum from n equals 0 to infinity, negative 1 to the n, root pi over 3 all to the 2n, all over 2n factorial. That is the Maclaurin series for cosine with root pi over 3 plugged in. And though you're not going crazy, that's not something that you can evaluate nicely without a calculator, so the answer is just cosine of root pi over 3. Had that exponent said 2n, then we would have just had cosine of pi thirds. Well, before we do this one, let's write it in a summation notation. It says the sum from n equals 0 to infinity. There's definitely a negative 1 to the n. Looks like e to the n over n factorial, which is the same thing as the sum from n equals 0 to infinity, negative e to the n over n factorial. This is the Maclaurin series for e to the x with negative e plugged in. So this is e to the power of negative e, or 1 over e to the e. That's what this series sums up to.